The Bruijn graphs are a completely different approach to genome assembly and present one of the few tractable algorithms for assembling short read data. This is one of the most difficult concepts to grasp in assembly. We start as usual with a genome that's sequenced to obtain a set of reads. The key thing to understand about this approach is that we divide each read into a set of overlapping words of a standard length. We refer to the length of these words as k and the words as kmers. In this example, we're dividing each read into kmers of length 3, or 3mers. As you can see, some kmers occur more than once, like AGC and CAT, and we can reduce the set of kmers so that each kmer is represented only once, so it's a set of unique kmers. Then, we can begin constructing a graph, our de Bruijn graph, where each kmer is a node, and edges between the nodes show where one kmer follows on from another. So, starting at ACG on the left, we can link that node to CGC because ACG ends with CG and CGC begins with CG. We can continue in the same way to link CGC to GCA and GCA to CAT. However, when we try to connect CAT to the kmer that follows it sequentially, we find that we have three choices. Because the original sequence had a repeat, GCAT, that occurred 3 times, there are 3 possible ways to move forward from the node CAT. The next kmer could be ATC, ATG, or ATT. All 3 of these begin with AT. As a result, we draw edges between CAT and each of those 3 kmers. Now we can continue as before for each of those paths. So we link ATG to TGA, which then doesn't link to anything else. But we can go back to ATC and link forward to TCG, CGG, and GGC, then back to GCA, and here we're going to add the GCA to CAT link just for demonstration. And similarly, we can link CAT to ATT, then to TTA, TAG, AGC, and back to GCA. Again, the GCA to CAT link is only for demonstration. At this point, we've constructed our de Bruijn graph, and now we have to find contigs using it. The way we do this is to find something called an Eulerian path. This is a route that follows the arrows in the de Bruijn graph and touches each of the arrows only once. In reality, it's not usually possible to find a single path that does this because of the repeated regions in the sequence, so we end up finding multiple paths that correspond to contigs. To begin with, we start at the entry point on the graph, like ACG here, and we keep the link to the next kmer, so our new sequence is ACGC. Then we move on to the next edge and include GCA in our growing sequence, which now becomes ACGCA. Now, it looks like we should be able to include CAT in our growing sequence. But this isn't possible, because we don't know from the kmers alone whether the link between GCA and CAT truly exists on the white path after ACGCA on the genome, or if it only exists on the green path, GGC, GCAT, or the blue path, TAG, CAT. So we stop extending our contigs after the kmer before a branching point. Here we stop at GCA. This gives us our first contig, ACGCA. We can then repeat this process starting at a new entry point. In this graph, there's only one entry point, CAT, and we can take any of the 3 paths that flow from it. We choose to follow the green path first through ATC, TCG, CGG, and GGC to finish again at GCA. The path stops there, so we've identified the contig CAT, CGG, CA. Then we repeat the process until we run out of paths. The next path starts at CAT again and links ATG and TGA to give the contig CATGA. And finally, we complete the path from CAT through ATT, TTA, TAG, and AGC to GCA, giving the contig CATTAGCA.